Hi, Rodrigo. Hi.
Hello,
Hey, hello. Can you
can you hear me?
yes, can you open your presentation in the full screen mode?
Oh yeah, I'm afraid cannot do that because then I will lose my notes.
Ah,
Is
okay.
that fine if I just move away?
Okay. So,
Okay, let me just.
so yes. Is it okay for you?
Yeah, it's fine.
Okay. Let's start. So now we are starting the third day of our school with a lecture of Rodrigo Nogueira, who is a PhD student of Kyung-Hyun Cho in New York University, and he will present talk on the topic of learning to query. So let's welcome Rodrigo on our school. Okay, you can start.
All right, yeah. So let me begin. So yeah, thanks for having me. Yeah, so my name is Rodrigo, and I'll talk about a work I developed with my advisor Kim Cho at NYU. So yeah, let me begin by stating a dream that probably many of us have in this field of artificial intelligence, that is to build an agent that can correctly answer any question, no matter how complex it is. But however, training such an agent to learn all the human knowledge might be very difficult. For example, if you think about a neural network, it needs to have a huge number of ways to be able to remember all this information that we already produced through centuries. So we might not want to learn everything, but rather have a mechanism to access this knowledge, which in turn can be stored in some traditional way, such as text or image. Uh, a little bit of related work in this area. There have been some attempts to make a neural net to access external knowledge, such as memory networks, neural Turing machines, and attention mechanism, mainly used for neural machine translation. However, these methods do not scale well with respect to the memory size, as roughly speaking, they need to compute a score to each knowledge item at running time to decide if an item will be used or not. So if you have, in our case, millions of documents that you want to inspect, if you use one of these methods, you either have to compute a score to decide if you're going to store them in a local memory, or you have to score all of them at running time and in the bit score in the case of attention mechanism. So to address this issue, we propose the following system, which we call a research assistant. In this approach, we give a question to the system, and it searches the internet looking for related information. It then produces an answer based on what it read, something like depicted in this figure. There will be a search module that will give us back some documents with respect to the query. And these retrieved documents can be used multiple times to refine the search by the search module. And then there will also be an answer module that will create a summary of the retrieved documents with respect to the question. So this is more or less an instantiation of that more broad dream. But in this talk, we'll focus on the search module part only. So our first attempt to implement a scalable search module is in the form of automatic web navigation system. The idea is the following. We see the internet as a directed graph, where the nodes are the pages and the edges are the hyperlinks, such as the one here depicted in this figure. And the task is as follows. We give a query to an agent. We place this agent at some starting web page. Ideally, this web page must have many hyperlinks, so we'll make the task of our agent easier to navigate. And this agent has to navigate the web by following hyperlinks until it finds the document that contains the answer. And here's an example. We give a complex query, such as a question in the form of Jeopardy questions, this famous TV show. For the last 8 years of his life, Galileo was under house arrest for espousing this main theory. And then we place this agent at the Wikipedia's main category page, which has links to many other categories and so on. And then the agent has to follow the hyperlinks until it finds the article that contains the answer, which is, in this example, is Nicolaus Copernicus. When it arrives at the page, it issues a special stop action, telling us that the answer was found and lies in that document, that the last node that it visited. So this is more or less our web navigation system. It can be seen as a reinforcement learning problem, in which the environment is the internet. The agent's actions are to decide which hyperlink we will follow, and the states perceived by these agents are the textual content of the web pages. A positive reward is received and the correct page is reached. So it's more or less what is depicted in this figure. And we implemented this agent as a recurrent neural network that takes as input the query, which can be a vector representation of this query that can be average word embeddings of the words present in the query. The previous hidden state is also taken as input. And this previous hidden state can be computed by some vanilla LSTM. And the vector representation of the current page, which can also be simply the average word embeddings in that page, or some more fancy attention mechanism as well. And then the agent will assign a score or a probability to each hyperlink and will follow the one with highest value. These scores, they can be computed as a dot product between the current hidden state, HT, depicted in the figure, and the vector representation of the page that these hyperlinks points to. And again, this vector representation it can be as simple as the average word embedding of the page. And once these scores, these dot products are computed for each hyperlink, we simply apply a softmax and take the one with highest probability. We also have here a probability to the stop actions, P of new here depicted in the figure. If that one is chosen, the agent stops its navigation. So this agent can be trained with supervised learning. Since the starting node is fixed and we have the answer node, we simply compute the shortest path between these two nodes to get a sample path to our training. We then train this agent to assign high probabilities to these paths. There is also the stop action, which must be chosen when the agent arrives at the answer node. We tried with some reinforcement learning algorithms, but they were not equivalent to the simple supervised heuristics that we came up with the shortest path. So in the end, supervised was as good or better in most of cases than the reinforcement learning algorithms. So, and we evaluate our agent in the Jeopardy dataset. It has approximately 120K questions for training that were extracted from the Jeopardy TV show archive. It also, of course, contains the answer. And the answer in our setup is the Wikipedia article whose title matches the answer from our database, from our archive. So as you can see from this table, our neural network agent is better than classical search engines such as Google. Of course, we have to take these results with a grain of salt, as our agent was trained on Jeopardy, whereas Google was not. The general purpose search engine, whereas our agent might not work well with queries other than the ones from Jeopardy. We also evaluated against some simple search engines such as Lucene, and yeah, our agent was by far the best. These results are nice, but Wikipedia is a semi-structured, well-linked, and clean corpus, whereas most of the web is not. So this approach might not work well if we go to the wild web. And then we came up with an idea: what if we simply use a search engine to access this external knowledge and provide the documents or whatever it retrieved back to some answer module or answer machine? And the current search engines, they work well if the query is precise and short. In this slide, the user wants to retrieve the famous Nature paper from DeepMind that describes the AlphaGo system. As you can see, the desired document is retrieved as the top result. So the search engine is successful in retrieving what the user wants, in this case, Google. However, if the query is vague or too long, current search engines have trouble in retrieving the correct document. For example, this query, artificial intelligence paper, Asian board game, is equivalent to the ones in the previous slide. But it is much longer and contains some imprecisions, such as Asian board game instead of Go game, and Google instead of DeepMind. In this case, the correct document is not on the top results, but it can be found as a link inside the third retrieved page. But the users still have to click on that, read all the information until it finds the paper. And this is not an ideal situation. It gets even worse when more complicated questions are issued. So this is often called the vocabulary mismatch problem, and refers to the fact that terms used in queries are often different from the ones present in the documents. And this leads to our next attempt to create a trainable and scalable search module, query reformulation. To solve this vocabulary mismatch problem, we can use the following framework. The original query is used to retrieve some documents. These documents are fed to a reformulator together with the original query. This reformulator can use these two inputs to generate a new query that will hopefully retrieve more relevant documents. In this example, we take this noisy query, artificial intelligence paper, Asian board game, retrieve some documents, these top four, give it to the reformulator together with the original query, and the reformulator hopefully will output this DeepMind Go paper query, and then we can query the search engine again and retrieve the top result. And this process of retrieving in documents and reformulating a query can be performed multiple times. But one might ask, why do we need to retrieve a first round of documents? Can't we simply reformulate the original query without this extra document information? Well, in theory can, but queries can be so diverse that the reformulator would have to know the words and concepts that are related in order to produce a good reformulation. This would bring us back to the problem of compressing the word knowledge in a single network, which is not scalable. Hence, these retrieved documents provide some guidance or clues on how the original query is related to the other pieces of knowledge, and can make our life of the reformulator's life as a little bit easier in selecting terms. So we can train this reformulator with reinforcement learning. For that, we need a data set of question and relevant document pairs. The reward to the reformulator is some metric that tells us how many relevant documents were retrieved. Those metrics can be recall, map, or NDCG. There is also, of course, this score component that will give back the reward, and then we can train the algorithm this way. Here's an illustration of our reformulator. The original query is encoded by a CNN or RNN and max pooled so that we end up with a fixed length vector representation for the query, represented in the figure as phi A of each. Similarly, the candidate terms, that is those terms from the first round of retrieved documents, plus the original query, they can be encoded with another CNN or RNN. So each term will be represented by a vector that contains context information, that is the words surrounding this term. And this would produce the phi B E of I term. And these two vectors, the vectors for the query and the vector for the term, can be fed to a binary classifier that will decide if the term should be used or not in the reformulated query. There is also a baseline network or value network that will predict the reward for those terms. This network is only used during training, and yeah, I'll explain next where exactly it fits in the training equation. So this model is trained with simple vanilla reinforce, where the cost is the reward, for example, the recall, minus the predicted reward by our value network, times the sum of minus log probabilities of all selected terms. The cost for the baseline is simply the L2 distance between the predicted reward and the real one. The gradients from the baseline network are not backpropagated to the rest of network to prevent some co-adaptation between the policy and value networks, as this might lead to some chaotic behavior. It's a little bit similar to the same trick they apply on the Atari Q-learning paper from DeepMind, that they freeze the target network for many iterations and only update them after these any iterations. So it prevents this co-adaptation. And I'd like to open a parenthesis here to mention that Google published recently a very similar model. In their work, the model reformulates one term at a time using an RNN, whereas our modules select terms independently of the ones previously selected or that will be selected in the future. I will show in the results slides how the performance of this sequential model from Google compares with the model that selects terms independently of each other, such as the one that I just presented. We also implemented a supervised method inspired by the work of Coe et al. In order to create a labeled data set of correct terms, we add one term to the original query and measure if this extra term increases or decreases the reward. If it increases, we mark this term as positive. Otherwise, we mark it as negative. For example, the original query is Google Asian board game paper, and it has a recall of 0.4. If we add the term DeepMind, it is a candidate term that were retrieved from the first round of documents. So if we add this term DeepMind to the query, the recall increases to 0.45. And therefore, we label DeepMind as a positive term. And we do that for all the terms, candidate terms retrieved from the documents. After collecting this data set of positive and negative terms, with respect to the query, of course, we then train a binary classifier to predict if a term will increase or decrease performance in case it's added to the original query. Then we concatenate to the original query all the terms predicted as positive. And this will be our supervised method. With this method, we can also come up with a trivial upper bound performance. And this will be a classifier that perfectly select all positive terms. And we'll see later how our models perform in comparison to this supervised oracle. So we are also interested in measure what is some upper bound performance for this framework that of retrieving documents and use these candidate terms. For that, we introduced a reinforcement learning oracle, and it works as follows. We split the validation or test set into small subsets, each with, let's say, 2,000 samples. Then we overfit this RL model, one RL model per subset, and measure their performance. The oracle performance will be the average reward over all subsets. This, of course, is a conservative upper bound, as it might be better reformulation strategies that these models were not able to find. But nevertheless, we are able to get some rough estimation if our framework is promising or not. And now I'll briefly describe the 3 data sets that we use to train our models. The first one is the TREC dataset, which is currently using a competition organized by NIST. This dataset was automatically created from Wikipedia. The input query is the concatenation of the title of a Wikipedia article with one of its sections, of one of its section title. For example, Sea Turtle is the name of the article, and diet is the title of one of the sections within that Sea Turtle article. So we concatenate Sea Turtle with diet, and this will give us a query. The ground truth documents are the paragraphs within that section, the diet section. So therefore, each paragraph in our corpus is considered as a document, and the search engine will retrieve them instead of the full article. And the goal here is to retrieve the paragraphs that are inside the section whose title was given as a query. This will be our TREC dataset. There is the Jeopardy dataset that I mentioned previously. It's the same thing. We give input a Jeopardy question, which was extracted from the archive. And the desired output is the Wikipedia article whose title is the answer to the question. And by the way, it turns out that 95% of Jeopardy questions can be answered using Wikipedia titles. So our approach works because of this particular setting of the Jeopardy questions. And these are hard questions, as you can see. They are designed to make interpretation not straightforward. And our last data set was automatically built by extracting papers, academic papers from Microsoft Academic API, which is pretty similar to Google Scholar. The input is the title or abstract of a paper, and the goal is to retrieve all the papers that should be cited in that paper that has that title. For example, here we have that famous ImageNet paper from AlexNet paper, sorry. And the goal is to retrieve all the papers that were cited in the AlexNet paper. We collected, so here's the summary of the data sets. As you can see, we have hundreds of thousands of queries and document pairs, which makes them suitable for deep learning approaches. And here's some results. We compare the performance of our models depicted by supervised and reinforced in the last lines with some other classical approaches, such as pseudo-relevance feedback, where the terms are measured with its TF-IDF score, or by some word-to-vec distance with respect to the original query. As you can see, our reinforced method is clearly superior. But the Oracle, the interesting thing is that the Oracle shows that there's still a lot of room for improvements. Both supervised Oracle and the Oracle for reinforcement learning show that we can still improve the performance of our system by a large margin. And in this slide, I show the performance of different RL models. The one with RNN encoder is a little bit better than the CNN encoder. And the sequential generator, the one from inspired by the Google paper, is a little bit worse than our independent generator, but it selects 3 times less words on average, which makes it a faster retrieval, and therefore it's more suitable for production implementation. And here I have some qualitative results. I show the probabilities assigned to some terms by our reinforcement learning CNN model, CNN encoder model. As you can see, there are 2 queries here, and they are the top 10 retrieved term assigned probabilities to the terms are related to the original query, whereas the bottom 10 are not that much. And we can also see the model still selects some common words such as the, or and, or and. So, and this is simply because we do not, these are neutral words. They neither increase nor degrade performance. And we don't punish the selection of these extra neutral terms in our reward formulation. And here's some examples from our Reformulator. You can notice that in this first example, one of the terms selected, chalet, is the actual answer to the question, which makes us think that the best reformulator to a factoid question is actually the answer that will retrieve the best document for it. And in the second example, it can select some related words to homelessness in Canada, public policy, but it still selects some noisy terms, some bad terms such as California. And yeah, this is something that surely can be improved. So yeah, in conclusion, our Oracle showed that there's still lots of room for improvement. And the good thing about this framework is that of practical use, since commercial search engines, they have click-through data sets, the one that the user queries and the clicks that a user made in the return documents. So they can leverage this kind of information to train such a system. And but we still need to improve the sample complexity of these reinforcement learning models, as it takes a lot of time to be trained. In our case, it's approximately 10 to 2 weeks just to get to these results. And as the Oracle shows, if we let them train longer or we have more computational power, we might increase their performance. And right now, querying the search engine represents 40% of training time in a distributed version of Lucene, and we can improve that as well. So, and this concludes my talk, and I'll be happy to answer any question you might have.
Any questions? I have one question about your whole system. Can you go to the slide where you show that these 2 parts then is like searching for answers, searching for resources, and another is for the generation of answers. I would like
Let me
at the
see.
beginning of the presentation.
You mean this one?
At the beginning, at the very beginning, where you're saying that the topic of this presentation is to select part of the system which selects, which reformulates queries. Yeah.
Okay, maybe this. Let me see. This one or?
Yes. And so
Okay.
I would like to ask you, can you give us more details about the answer module? What you are planning? Is it already implemented, and what is the purpose of the whole system? Not only this search and reformulation part of it.
Sure, sure. So yeah, we are actually working on the answer module right now. So the purpose of the whole system is that we have many documents, and we don't have time or the resource to read all of them, given our information needs. So the search module will only provide some documents, but the horsepower will be actually in the answer module that will be able to summarize some selected documents with respect to the query. One thing with this answer module is that if the question is complex, you might have many different answers. So if you train this model to simply, with supervised learning, let's say you have a data set of question and answer pairs, and you train this answer module simply to match the ones that you have as ground truth. That might be really hard because there's so many other different ways that you can answer a question, a complex one especially, that your model might not be able to learn any meaningful behavior to answer these complex questions. And this is, I'm talking about the abstractive summarization, which is you make a summary of a given query and you produce one word at a time. But there is another approach that it looks more promising, which is simply the extractive summarization, that we can select sentences from the retrieved documents and build an answer, and then compute a score of the answer provided by this module with some ground truth ones, and compute some reward, and then we feedback this reward to the module. So the module, this answer module, first select answers, and then later it can make a summarization more fluently by then applying an abstractive summarization, which you will then try to match our ground truth answer. So that might be what I'm trying to argue here, is that this answer module might need two steps. The one that first selects sentence from the document will force them to use the information provided by this document and make these answer more fluent through some abstractive summarization that will produce one word at a time.
Do you plan to have something like interactive refinement via dialogue with the user of the query? So it's like that your search model get some results from web search, then summarize it or analyze it in some way, and then decides that it needs to refine the query from user and ask specific question which will allow us to produce better summarization even without presenting results of the search to the user. Do you plan to do this, or maybe do you have any ideas about how can this be implemented, or maybe it is useless for your system?
Oh yes, certainly having a user in the loop will help a lot. Right now we have this problem that we don't have a large data set of complex questions and some long answers. And collecting those might be really hard because, as we're talking about, there might be multiple different answers. So putting an user in the loop during training of this full system might be a good idea, so it can guide and maybe make better use of our money spent collecting this data set. There is some interesting work from Percy Liang, a professor from Stanford, that he puts this, he creates a reinforcement learning agent that uses queries the user only when it's not sure what is the label for a particular input. So, and in the reward that he gives to the system, he tries to minimize the cost and minimize the time spent to train the system. So yeah, it requires less and less question asked to the user, and this is all learned, so you don't have to hard code any specific procedure to collect this data set.
And another more technical question, why don't you use MS marker dataset? Because it contains like human formulated question, human formulated answer, which is based on the collection of the snippets from the web resources which were output of Bing search engine.
Oh yeah, so yeah, that's a good question. We didn't use it, but yeah, we're trying to use it right now. Yeah, but that's one data set that we missed for sure. It's I guess the problem, if I remember correctly, the problem at that time that we didn't use is that they didn't have a fixed corpus that we could index in our search engine. But yeah, there are some ways that we can countermand that.
Okay, any other questions? No? So let's thank Rodrigo for his presentation.
All right. Thank you very much.
Hey, thank you, Rodrigo. See you in Amsterdam.
I'll see you. Thank you. Bye-bye.
Bye.